So today's lesson is on geometric sequences. But before we move on to that, let's do a little bit of warm-up, a review of arithmetic sequence. So an arithmetic sequence, again, is a sequence of terms where there's a common difference between each of the terms. In other words, they're going up or down by the same amount. So here we know that's an arithmetic sequence, and we're told that the recursive formula in this case is t of n is equal to t of n minus 1 plus 3. In other words, for a given term, it's going to be the previous term plus 3. But with any recursive formula, we sort of have to be given that initial starting point for it to be complete. So in this case, we do not know what t of 1 is, but we do know that the 53rd term, or t of 53, is 267. So how can we determine the first term? Well, it's a bit of connecting what a recursive formula is, known as an arithmetic sequence, and that since our terms are going up by 3, in other words, a given term number is the previous term plus 3, we should recognize that this is actually the common difference is 3. So let's take a general formula, or general term. That's going to be t of n for arithmetic sequence again. It's going to be a plus n minus 1 times d. So here we could say that n is 58 because, or sorry, 53 because we're told what the 53rd term is. So t of 53 is a, which is the first term, which is what we're looking for, and then n is 53 minus 1 times d. And then t of 53, we're told is 267. That's the 53rd term. A plus 52, and I should have filled this in already before because we know what d is. So it's going to be 52 times 3. So 267 is a plus 52 times 3 is 156. And then a is going to be 267 minus 156. So in this case, this gives us a as 7 minus 6 is 1. 6 minus 5 is 1, and 2 minus 1, so a is 111. So therefore, t of 1 is 111. So that's how we go through that example. I kind of like it because it sort of makes us connect recursive formula with the general term. So today we're going to move on to what a geometric sequence is. So we have to define and understand what a geometric sequence is. And then to the practical side, once we're given a sequence, determine first of all if it's geometric or not. So we obviously need to know what the definition of that is, and if it's so, determine what the general term and the recursive formula of a geometric sequence. So let's look at an example. So in this case, we have a sequence of 6, 12, 24, 48. Is it an arithmetic sequence? Well, let's look at the differences. The difference between the first and second term is a 6. Difference between second and third term is a 12. So immediately I could tell that it's not arithmetic because it's not a common difference. But we do kind of see a pattern in there. So what are the things that we could say about this sequence? The first term, let's state the obvious. The first term is 6. Another thing that we could sort of detect in here is that as we go to each sequence, it's the previous term doubled. So we're taking each sequence and multiply, so each term and multiplying by 2. So as the term number increases, the next term is the previous term multiplied by 2. Okay, so that's almost like a recursive definition or a recursive explanation of that that goes on. The sequence doesn't end. And we could come up with other things, but really that's sort of the most three important things. Really, these two parts are the most important part. And in essence, we've kind of defined what a geometric sequence is. So let's go off and look at how we determine a recursive formula or a general term. So the recursive formula might be the easiest one since I already described it. So the first term is 6. And then we said that the subsequent terms of t of n is really the previous term, so t of n minus 1, and we're multiplying that by 2. So this is for n is greater than 1. The general term might be a little bit more tricky, but kind of try to figure out what it might be. We know that things are being multiplied by 2. So here we could say that this is going to be 2 to the power of something, but 2 to the power of what? So here we can kind of say that t of n, recognize that the first term is 6, so we might have to start off with 6. And basically because things are being doubled or every single time, in other words, we're doing multiply by 2 over and over again, really it's going to be 2 to the power of something. So that's what we sort of recognize. So in this case, we're going to have 2 to the power of n. So let's try 2 to the power of n. Well, what happens if it's the first term? 2 to the power of n is 2, and 6 times 2 is 12, which really gives us the second term. So we're off by 1 in essence, and what we really want to do is, because we have the first term here 6, we want our power to evaluate to 0. So given that it's the first term, we really want to take 2 to the power of n minus 1. So that's what we want to do there, and that's how we can come up with the general term. So let's look at this in general, of what a geometric sequence is. So a sequence that has a common ratio r. So in other words, you take one term and divide by the other. Sort of like looking at the common difference, we're going to take one term and divide by the previous term to figure out what that ratio is. So there's going to be a common ratio between the consecutive terms, and stating a bit of the obvious that the ratio cannot be 0. So here, if we're given a geometric sequence, and we know that the first term is a, and r is that common ratio, and n is the element of natural numbers, a geometric sequence can be defined in several ways. First, we have the general term. So we sort of explore that in the example up above, where t of n is going to be the first term multiplied by r to the power of n minus 1. So we have to offset it by 1, so to speak. The recursive formula is actually a little bit more straightforward. We say that t of 1 is that first term, and then the current term is going to be the previous term, but we multiply by our common ratio. And this is for all n greater than 1. And if we want to write this in function notation, we say that this is going to be f of n is equal to a times r to the n minus 1. So there's a strong correlation between function notation and the general term, and as I sort of expressed in the first section of this unit, when we write the general term, it's implied that we have a sequence. So let's look at some examples. We want to write the first 3 terms of each of the geometric sequence. So t of 1 is just going to be 5. That's going to be our first term. Actually, you know what? Let's just write it as a sequence. So we got 5. Well, when n is 2, we're going to take 1/3 to the power of 1 times 5. So that's going to be 5 over 3. And hopefully we can see that the pattern here is that we're taking each subsequent term and we're dividing it by 3 or multiplying by a third. So the third term is n. N is 3. So n minus 1 is 2. So it's 1/3 is 9. So 5 times 1/9 is going to be 5 over 9. The next sequence, we're given the first term and the ratio. So this one is actually relying on a bit of the recursive formula. And this one is a lot easier to do. Hopefully you kind of recognize that once given a recursive formula, it's easier to list out the sequence as opposed to looking at the general term all the time. So the first term is 25, and the common ratio says that we're just taking each term and we'll multiply it by 4 to get the next term. So 25 times 4 is 100. The next term is going to be 4 times 100, which is 400. And if I want to do the fourth term, 400 times 4 is going to be 1600. And that can continue on. I should have said the first one. That can continue on as well. For the next question, let's look at whether we're given a sequence. Let's examine whether it's arithmetic, geometric, or neither. And then if it is, then we're going to write the general formula. for each of the sequence. So here we're looking at 7 to 6, so that's a common difference of negative 1. 6 to 4 is negative 2, so immediately we could rule out that's not arithmetic. We could divide, so 6 divided by 7 is 6/7. 4 divided by 6 is 2/3. That's not a common ratio, so therefore it's going to be neither. The next one, here it goes from negative 2 to 2. That goes up by 4. So 4 to 6 is another common difference of 4. And 6 to 10 is another difference of 4. So here we can assume there's a common difference of 4. So here we're going to write out the general term as an arithmetic. So this is an arithmetic sequence. So the general term is going to be, again, negative 2 plus n minus 1 times d. So the common difference here is 4. And let me just rewrite that a little bit cleaner. So negative 4 plus 4 times n minus 1. If you want to expand this out to be simplified, you can as well. For the next question, well, I could easily see there's not a common difference. And in this case, that it is going to be common ratio. We can see that going from 1.5 to 15, if we're going to multiply that by 10, or likewise we do 15 divided by 1.5, that's the answer of 10. So there's a common ratio of 10. And in here we're going to have a common ratio of 10 as well, because 10 times 15 is 150, and the next term is 1500. So we do see a common ratio of 10. So this is geometric. So again, we just learned above, the general term for a geometric sequence is going to be T of n times a. I'll write it out. Since this is new to us, it's going to look something like that. So in this case, T of n is a, is in this case 1.5. Our common ratio is 10 to the power of n minus 1. So there's a general term for that third example. So in the next example, we told that we have a geometric sequence. So hopefully the numbers do jive and that there's a common ratio. So let's go off and figure what that is. And the common ratio here is negative 7.6 divided by 8. Negative 7.6. So here, let's say R is divided by 8 is negative 0.95. And let's double check the next one as well. Here we're going to do 7.22 divided by negative 7.6, and we do get negative 0.95 again. So that we can say that the common ratio is negative 0.95. So the general term for geometric sequence, so let's write it out again so it sticks in our head. A times R to the power of n minus 1. So in this case, the first term is 8. And my common ratio is negative 0.95 to the power of n minus 1. The recursive formula for this sequence, so T of 1 is going to be 8, and then T of n is going to be negative 0.95 times the previous term of T of n minus 1, and for all n greater than 1 in this case. To calculate the 10th term of this sequence, we could either do one of two things. I could do the recursive formula 10 times, I guess, or 9 times, going all the way up to T of 10. That's going to be a little more difficult because the ratio is not straightforward or it's not an easy calculation. So I'm going to use the general term. So here I want to figure out what the 10th term is. So that's going to be T of 10 is 8 times, my common ratio is negative 0.95, all to the power of 10 minus 1, which is 10 to the power of 9. And we plug that into the calculator, we're going to get negative 5.041995. So that's going to be the 10th term. Keep rolling along. Here's another example that we could kind of be given. So here we're given the terms and we're told that it's geometric. 11, 13, 99. So let's quickly figure out what the ratio is. So it's going to look at the first one, 33 divided by 11. So here we're going to see a common ratio is 3. But we don't know how many terms there are. Hence the dot, dot, dot. But we're sort of given this last term in our sequence, or a specific term in our sequence. So how can we go off and figure out how many terms there are, or maybe more, another way we could phrase this is 5 612,659. What term number is that in our sequence? So we have to rely on our explicit formula. So T of n is equal to A times R to the power of n minus 1. We don't know what n is. That's what we're trying to figure out. But at least we know what T of n is. So T of n is 5, 2, 6, 1, 2, 6, 5, 9 is equal to the first term of my sequence is 11. We just determined the common ratio here is 3. And again, we don't know what n is. That's what we have to do. That's what we're actually calculating for. So here we're going to isolate for my power. So dividing by ourselves by 11 and dividing 52,612,659 by 11, we get 478,2969 is equal to 3 to the power of n minus 1. So how do we solve for our variable when it's an exponent? So if we go way back to when we did exponential functions, and with the enriched class we did logs, we could use our log formula to figure out what the exponent is. So remember, in general, if we have y is equal to b to the power of x, how we sort of the inverse of that, the inverse of exponential function is what we call the log. So in order to get x, we could say that that's going to be the log of the answer. In other words, log of y is equal to log of the base. So log base 10 in this case. So here we're going to say that n minus 1, because that's my exponent, is going to be a log of 4,782,969 over the log of 3, and we get n minus 1, plugging that in my calculator, or n minus 1, plugging that in my calculator, we're going to get 14. So in order to get n, we need to add 1 to 14, so n is going to be 15. So therefore there are 15 terms in the sequence. Okay. Here's a word problem that we can sort of take advantage of exponential sequences. Given the time that we're living in right now with the COVID-19, this example is a little bit relevant. Although it's not a bacteria, but we could kind of say, and then when we talk about modeling the infection rate, really what we're trying to say is that it's an exponential growth. The idea of R naught, so that's actually mentioned a lot in the news these days. We'll hopefully discover where R naught is coming from, and really they're talking about R initially. How many? What's the ratio in terms of how fast the infections are growing, or how many people are being infected? So here we're taking an example of a bacteria. It's going to double every 14 hours. So here we can apply that our R is going to be 2. And every 14 hours. So we're going to start with 100 bacteria. So here that we can assume that that's going to be my A value. How many would there be after 17 days? So we have to do a little bit of calculation because it's not very straightforward. We need to convert days to hours. So 7 days is going to be 7 times 24 hours. So that's going to be 168 hours. So given 1 week, 168 hours, but it's not doubling every hour. So that's not my n value. To determine my n value, in other words, how many times is it doubling, we're going to have to take 168 and we're going to divide it by 168 hours divided by 14 hours. So really this is going to double. So 168 divided by 14 is 12. So really we're saying within the span of 7 days, this bacteria is doubling every 3 days. If you've been listening to the news, that's how they're sort of tracking a little bit what's going on with the COVID. So I remember one news segment, they were talking about every 3 days, they recognized that the number of people that were contracted COVID, the number of positive cases was doubling. So that's quite a bit alarming. Every 3 days it's doubling. And that's what they're trying to say. We want to flatten that curve. They want to sort of lower that. And then as time passed on, and then I read on the news or heard on the news today that it was a lot longer now. I think at that time it was maybe 5 to 7 days for the number of cases to double. So that was a good sign. That means all the things that we're doing in our physical distancing and everything is taking effect, because really our R value, when I think about it, has sort of reduced if we want to think about it based on the number of daily infections, because it went from basically 3 to 5. So that's what's sort of happening here. It's going to double 12 times. So let's come up with a recursive formula. So T of n is going to be A. In this case, so I'll just write out the formula again, so we're kind of used to it. So that's a geometric sequence. So T of n, A is 100, and it's going to double. In this case, it's going to double in 12 minus 1 times. So really we want to know how many times, what's T of 12. So that's going to be 100 times 2 to the power of 11. And that's going to be 100 and 2 to the power of 11. Well, 2 to the power of 10 is 1024. So 2 to the power of 11 is going to be 2048. So that means T of 12 is going to be 204,800, 204,800. So after 1 week or 7 days, that's how much bacteria we're going to have. The last example we want to take up is the idea of depreciation. So here we're going to have an R value. So if we think back to our exponential functions unit, when things are increasing, that's what we call increasing, the base is greater than 1. So in this case, we're going to have what we call decay, because the value car is depreciating. And here the R value is going to be less than 1. So that's what we're going to get sort of these from. So we want to determine an explicit formula for the value of the car at the end of year n. So I just sort of like to start off at the very beginning. This car is worth what? So maybe this is year. In the beginning, the car is worth 50,000. So in the first year, it says it depreciates 12% in the first year. So after 1 year, we could say that, well, we could take 50,000 times 0.12, and then subtract that from 50,000. But the net effect is that this is going to be the same thing as, maybe I'll write an equation here, it's going to be 1 minus the percent that was decreasing by. So this is going to be the same thing as 50,000 times 0.88. And this is equal to 44,000. So after the first year, the car is worth 44,000. The second year, and this is where our pattern will repeat, because every year after that, the car is depreciating by 8%. So the car is worth 44,000 after the first year. So after the second year, it's going to be 44,000, and in this case, multiplied by 0.92. And after the second year, after year 2, the car is going to be worth $40,480. And then we'll continue on. So we could recognize that here my R value is actually 0.92. What's my initial starting point? So in this case, that's going to be 44,000, because that's when it actually started depreciating by the same consistent 8%. So our general formula, if we want to come up with this now, is, again, it's going to be A times R to the power of n minus 1. So T of n is going to be 44,000. And my common ratio is 0.92. And then it's going to be, pretty sure, n minus 1. So let's confirm this. In year 1, how much is after year 1? So when n is 1, how much is this car worth? Well, n minus 1 is 0, so the car is going to be worth 44,000. So this looks like the formula is correct. For B, so how much is this car worth after 30 years? So we're looking at T of 30. That's going to be 44,000, 0.92 to the power of 30 minus 1, which is 29. So we take out our calculator. So after 30 years, this car is worth $3,920.12. So obviously after all that time, it has depreciated a lot. Question is this realistic? If you find me a car that lasts 30 years, you found an owner that took really good care of this car, probably never drove it. The likelihood of a car lasting 30 years is almost next to none. So this is obviously not realistic. So one thing to understand is this formula can only apply in a realistic way to a certain amount of time. And even if you look at what's happening right now with COVID-19, you could think of at the initial start, yes, everything is exponential, and it was interesting when I was watching the news today. They were talking about they want R naught to be less than 1 or something like that. Right now it's currently about over 1, or I think close to 2. They really want to drive R naught down. In other words, given one person being affected, how much is this exponentially going to grow? And realistically, eventually it has to flatten some point because there's only so many finite people who could actually get this disease. So it cannot grow exponentially forever. At some point, it has to sort of flatten out on its own because there's less number of people that are around that can be affected. So one thing to know in practicality is that given the general term, recognizing that it's only might be applicable for only part of the cycle that we're looking at. All right, so that's geometric sequences. A little bit more tricky in terms of the math, but conceptually, hopefully, it's not too much different than what we saw in arithmetic sequence.